This semester, we're going to be doing mini projects, which are projects that will take place outside of class, but that will give you a chance to get some hands-on, maybe a deeper dive into some material, and it will also give you a chance to do neat work. That's one reason I really like these mini projects. They don't have the urgency of a quiz where you only have a few minutes to crank out an answer. With a mini project, you can write up your best work and submit it. I have specifications drawn up for how to pass everything in this class, how to earn a pass. And the mini project section is pretty big. So down at the bottom here, so for problems in mini projects, to earn a pass, they need to be free of various types of errors. You need to go and read through the specification section. It'll be well worth your time. But a couple more things. You need to be addressing it to the right audience. You need to be showing your work. And if you don't show your work, if you just write an answer, well, that's no good to me. I need to see your thought process. So take the time to write things out, use full sentences, use punctuation. Show me that you can communicate and that you own this material. And I'll show you where we're going to type this up, but ultimately you're going to be submitting a URL in Canvas to your final homework page. I want to specifically mention graphical elements. You're going to be importing images, often of a graph, and in that case, it needs to be well labeled and visually clear what idea you're trying to get across. I do not want just a screenshot of cells in a calculator where a calculation took place. Take the time to type things out. So go through the specifications of the assignment and learn how to get a pass for everything, but on these mini projects, the bar is set higher than on most other components of the course. There's an editor called HackMD, so hackmd.io, where you will be typing up your solutions to these problems. Right now we're seeing the view of the list of problems where you'll actually get your problems to type up. But I want to show you here in the editor that there's the text editor part and then the output part. And what you see here is the text that shows up over here. So create a free account at this web address that you will use throughout the semester. That showed up here. And it all got typeset nicely. Down here, you actually see where I created the links, and the two try to stay in sync for the most part. To some extent, you might just want to go clear to the editor pane and ignore what the output looks like for a while. Sometimes you'll like it to be split. And now it's time to show you how to make those. So the instructions here at the top said you go to menu, import gist. So that's what we're going to do. We're going to menu. We're going to put, so there's export gist. That's not what we want. We want import gist. If we click on that, it asks us to paste a URL there. And the URL that we would paste for mini project 1 is this one. We would paste that and hit import, and it would show us mini project number 1. Mini project number 1 is about partial fractions. So I'm going to go through all of the various mini projects, but you probably don't want to watch that portion of this video until we've actually reached the part in the semester where we've covered the materials so that these will make sense to you. So feel free to stop watching at any point in time. This video is not meant to be viewed all in one sitting. All right, for partial fractions here, I am giving you the chance to do a little more detailed dive. We're only spending a couple days on partial fractions, and there's no way that we're covering the full theory, and we're getting as much practice in as we would like. So we get to do that in this mini project. And we've got a table here reminding us how if you have factors of a certain flavor, then what the corresponding partial fraction decomposition needs to look like based off of just that factor. And then there are two problems. Yeah, two examples and then 2 problems. Now, I want you to notice that I'm asking you to actually find the full partial fraction decomposition for these functions. Up here in the examples, I just told you the form that it needed to be in, but for the two problems you're going to do, you're going to find the values of A, B, C, D, and E, and yes, you're going to type it up. But wait, how do we do such math type? Let me show you. So in the editor here, you can see how I got the code for these. So problem number 1 here, the bold actually came from these little underscores that I placed here, but you'll notice that the math input was placed inside of double dollar signs. And yeah, I've got some sample text here. So if I put the math code between single dollar signs, it stays inline, but if I change it to double dollar signs, then it jumps into display mode. So that's just an example of what can happen. All right, so but how do I get this? This code looks mighty difficult. Well, my recommendation would be you can either learn LaTeX or you can just type it into Desmos. And in that case, once I've typed it in, I can copy an entire cell, and then when I paste it back in over here, I just need to make sure that I put it between dollar signs if I want it to display. So add the dollar signs on each end and it will display in math mode. Without the dollar signs, it will just look like the text. So you're going to fully type up your solution for each of these problems. Wait, there were 3 problems. I'm just not very good at counting. I didn't scroll far enough. So the 3 partial fraction decomposition problems. And let me read more carefully here. For the first problem, I said actually find the full partial fraction decomposition. For problem number 2 and problem number 3, you don't have to do it. You can leave it in the correct form of the answer. So leave the letters A, B, C, D, and so on up top. Good luck. For mini project number 2, numerical methods of integration, we've learned all about Riemann sums, midpoint Riemann sums, trapezoid Riemann sums, and even Simpson's rule at this point in time. Now it's time to put it into practice. And unlike on the quiz and other things we've done in class, I'm asking you to do it with a lot of rectangles. So I'm asking you to find the value of an integral, and then we're going to approximate that integral using a Riemann sum with 100 rectangles, left-hand Riemann sum with 100, trapezoid, midpoints, and Simpson's rule. There's no way you're going to want to do that by hand, or for that matter, even type it out. You're going to want to use Desmos, and that will involve coming here, and if you type the word sum, or if you go down into the palette below, you can find it, and you'll be able to actually write up a formula. And no, I'm not going to write it up for you right now, but you want to use sigma notation, but let Desmos do the work for you. But also, I don't want to see just an answer. I want to see the formula. I want to see the work. And Desmos will tell you how to typeset it, but it'll also give you the number. Don't just take a screenshot of what you did in Desmos. Good luck. All right, for mini project number 3, we're asked to find the surface area of a pond. And for this one, we're just going to follow the instructions down bottom. There will be a link to a Desmos activity that you'll complete fully in Desmos. And there will actually be nothing for you to submit for this particular mini project, even though it shows up as an object with a due date in Canvas. Good luck. Mini project number 4. And for this one, we're going to estimate the volume of a football using the techniques of calculus that we've been using. So there's a link here to a graph that I'm going to open up. In this graph, what we see is a football that I've placed there, and I've tried to match the exact dimensions, and somehow we need to estimate the volume of this football. To do that, you're going to need to find some curve that approximates the ball and figure out how to rotate it so that you get the exact football shape that we all know and love. As you do that, you're going to type your work in here so that we can see your answers. And you'll be submitting this, right, for mini project 5, the length of the St. Louis Arch. We want to actually calculate how long is the St. Louis Arch, and we have a formula that approximates it. You'll need to figure out how to find the length of that curve, and you're going to do it inside of a Desmos activity. You'll use the code that this link contains. Your code will be different than the one displayed here. Good luck. All right, for mini project 6, we're going to learn another p-test. So just as a reminder, in class we learned the p-test. If we did the integral from 1 to infinity of 1 over x to the p with respect to x, then that would be a convergent integral if and only if p was greater than 1. In this mini project, we're going to look at a different style of integral that also has a p in there, and we're going to try to decide when does this integral converge and when does it diverge. We need a full classification for what values of p will this be a convergent integral. Good luck. Mini project 7 is a parametric maze. This one's more just a fun project where I'm asking you to solve a maze, draw out the solution using parametric equations. I wouldn't consider it the most applied of projects, but it'll be some good practice for us. So we need to start up here. So using a parametric equation. So remember, you can always just enter them coordinate-wise, and Desmos will plot them. And in this case, we want probably just to go straight down. So in that case, 1.5 for the x values, and then we're going to go from 10, and then we're just going to go all the way down, so minus 8.2t. So in that case, I have a line that goes down. Maybe I'll change the color so it's easier to see. Then from there, I want to go over 1 unit. So I'm going to make another line segment. So I'm going to have the y value just be 0.8, and the x values are going to go from 1.5 over 1 unit. So the y values needed to be 1.8. Cool. So there's the next leg of my solution here. I need to trace this all the way down throughout the whole maze, and the hope is by the end we're going to be pretty good at these parametric equations. Good luck. All right, mini project number 8, converting between polar and Cartesian coordinates. So in particular, rewriting certain curves. Here I've listed the formulas that relate polar coordinates to Cartesian coordinates, and we want to complete this. It's going to be another Desmos activity, so there will be nothing to submit in Canvas. So you'll go into Desmos and you're going to try to solve for r here. Remember, y is r sine theta, x is r cosine theta, and then we're going to use our algebra kung fu to isolate the variable r once you've made that substitution. The first 2 problems involve converting from rectangular coordinates to polar coordinates, and the last 2 problems involve converting in the reverse direction. So in that case, remember, if you want to get rid of cosine theta, well, you'd better have an r times cosine theta, and that can then become an x. And similarly, sine theta, if you multiply by r, you get r sine theta. So my hint for this first one would be to multiply both sides by r squared, and from there, you're going to be able to substitute and get x's and y's in. And same with the last problem. Remember, you can always ask me for help, but good luck. Mini project number 9, talking about modeling our weight. We're going to be making up some numbers here. So say you were modeling your weight. You might as well make it somewhat realistic, but whatever. I'm not going to know or care. So we're going to let W of t be the weight t weeks from now, and we want to find an exact formula for W of t based off of a few assumptions. And we're going to just make up those assumptions right here as part of this problem. Everyone's going to have different numbers, and that's okay. Suppose that you follow your usual eating habits and eat like that from now on. How many pounds would you gain each week from food with no exercise whatsoever if you were entirely sedentary? So just a certain number of pounds you'd gain per week. Record your answer. Then, with your current level of physical activity, what portion of your weight do you think you lose each week? So you're exercising the way that you do now and you had no food, say, or minimal food. How much weight would you lose? Well, maybe you'd lose 2 or 3%. I don't know. Make up some number that sounds realistic to you. And now you're going to write out the differential equation that describes the change in your weight. Once you've written out that differential equation, you're going to make up an initial condition. And like I said, make up some fantasy weight or make up a model for your brother or something. It doesn't matter. And then once we have the conditions here, we have an initial value problem that you're going to solve. And then once you've solved the initial value problem, that'll give you a formula for your weight. I want you to find the long-term weight that you'd be approaching. So what happens as time goes to infinity? What is that equilibrium weight? Our mini project number 10 is kind of a fun one, geometric series. So I'm giving you some visuals and you've got to answer the questions. This first one says, find the portion of this figure that has been shaded. So not all of it has been shaded, but some portion has, and you can actually calculate that. Got 2 others here. Nice patterns, and all 3 of them have some geometric series in there, although I'll give you a hint that this first one is actually the hardest because the pattern doesn't fully hold. It's not actually a geometric series, although it has different pieces that are geometric series. But that's all the hint I'm going to give you. Good luck. All right, mini project number 11. You are going to create a lesson of your own. You'll be able to swap out your lesson topic here, and this lesson is going to take place in a text message format. We've got 2 people texting back and forth. One of them is going to be teaching the other one how to do one of the exam problem types. So you're going to choose one of the sample exam problem types and write a tutorial explaining what concept is being tested and how you might solve it. So you're going to end up replacing the text that's here, but read the text that's here because it tells you what you need to do to earn a pass. So for example, you need an explanation of the type of problem that's being tested, why it's important, a demonstration problem that's different than any example we covered in class, a full solution of your demonstration problem, and then any study tips or hints that will help a student to succeed on this problem type on an exam. Have fun with this. Have a good, realistic dialogue, and try to make it look pretty, but you can totally do it.